Hello, everyone, and welcome to another episode of the Data Science Decoded podcast. I'm here with Mike and Nir. How are you guys?
Hello, we are great. We are envisioning talking about very interesting paper which actually shaped a lot in the modern AI world. So looking forward.
Cool. Nir?
Never better. Everything is good. And looking forward to dive into the Perceptron.
Perfect. So you build it up. So I'll tell the listeners today's episode is the seminal paper of the Perceptron by Rosenblatt. It's called the Probabilistic Model for Information Storage and Organization in the Brain. So previous episodes we had like psychology stuff, right? And now again, it's in Psychological Review. The paper is from 1958. So it's interesting that a lot of seminal papers were published in various journals that are not like mathematically oriented. So a few words about Rosenblatt. It's Frank, his name. He lived from 1928 to 1971. And you can see here that it says he's from Cornell Aeronautical Laboratory. So it's interesting how everything was multidisciplinary before it was hype to be multidisciplinary. And he mostly did work on psychology, like we're going to see here, like brain science, neuroscience, and also computer science, combining those. So his work is like pioneering in artificial intelligence. And let's dive in. I'll read. So the idea here, we're going to concentrate on the introduction, then go over the main derivations, and also concentrate at the end on the conclusions and why he thinks the model is important. And we'll give also context compared to today and what we're doing as practitioners.
Daniel, question.
Yeah.
Is it true that Rosenblatt was both a psychologist and a computer scientist?
I don't know what from an education point of view. I don't know where he got his PhD, but his contribution was in those areas. So he tried to solve the problem that he's gonna say now. So he says here, if we are eventually to understand the capability of higher organisms for perceptual recognition, generalization, recall, and thinking, we must first have answer to three fundamental questions. Okay, so he raises three questions at the beginning of the paper. How is information about the physical world sensed or detected by the biological system? In what form is information stored or remembered? And three, how does information contained in storage or in memory influence recognition and behavior?
By the way, Daniel, we can ask exactly the same questions about modern LLMs, about modern neural nets, exactly the same question. And maybe the answers on these questions somehow shaped artificial intelligence as we know for today. Maybe if artificial intelligence had been taken in another path, maybe the answers on the questions were completely different. So these questions actually are extremely important practically to everything.
So not a lot have changed. And he says here, the first question, how information is being detected by biological system, he says is less relevant. It's more like in physiology sphere. So he's not going to go into that. The second and third question, so how the information is stored and how the storing information affects behavior is what he's trying to do here in this paper. And again, there is the concept of information that he's using without defining. So maybe it's what Shannon defined. I don't know. And he says,
by the way, we're coming across this concept in basically almost every paper that are talking, because information is one of most important concepts in machine learning and in statistics as well. So it's not a big surprise that we are coming across it every time, almost every time.
Yeah. So it's good that we went over Fisher. To the listeners, there was an episode about Fisher. Feel free to look it up.
The first one, by the way.
Sorry, the Fisher. Yeah, the first one of Fisher, and also Shannon. They both discussed information in a sense.
Yep.
Okay, so I'll continue with the introduction. It says, with regard to the second question, which is the question how is information stored or remembered, two alternative positions have been maintained. The first suggests that storage or sensory information is in the form of coded representations or images with some sort of one-to-one mapping between the sensory stimulus and the stored pattern. Okay, according to this hypothesis, if one understood the code or wiring diagram of the nervous system, one could, in principle, be able to discover exactly what an organism remembers by reconstructing the original sensory patterns in the memory traces which they have left, much as we might develop a photographic negative or translate the pattern of electrical charges in the memory of a digital computer. Okay?
Actually, it is quite interesting. I'm not sure I'm going to be correct on what I'm going to say, but when I read it, I thought about similar concepts for our current machine learning models, and specifically neural nets. And for me, for example, can we know what the machine learning model was trained on if we know all these weights? There have been some works on it, how we can reconstruct training data based only on the weights or only on the parameters of the trained machine learning model. And then I read it. I'm not sure I'm correct, but I think there is some similarity here. What do you think, guys?
I think, yeah, of course, there is a similarity. When I read it, what jumped into my mind is autoencoder. So the latent representation is the coded image, so to speak, and we can by having access to the latent representation, we can recover the image, the exact image in a one-to-one map. Now, I think that's what he's talking about here. But he's, I think, more even more primitive than what I just said, which is saying you store a negative of all the of all the images, like in a memory of a computer.
Exactly.
Which we know is not true.
True. Yeah. So that's what I wanted to say. Here he says the first hypothesis that is common back in the day. It's like the memory, like our memory is more like a computer, right?
Yeah.
So you have places that actually information or bits or whatever are stored on off, whatever.
Yeah.
And we know that it's not the case.
No.
And then he says this hypothesis is appealing in simplicity and ready intelligibility. And he says there's a few models that developed of this idea of coded representational memory. Now, the second hypothesis, the alternative approach, which stems from the tradition of British empiricism, hazards the guess that the images of stimuli may never really be recorded at all, and that the central nervous system simply acts as an intricate switching network, where retention takes the form of new connections or pathways between centers of activity. Okay, so the idea here, like when you see different images, it changes how the network interacts and how information flows in this network of whatever connections, neurons, etc. So I think this is more similar to what we believe today, but I don't know the current
I think it is similar. Consensus. You know, now I'm changing my mind. I think it is more similar. I don't know what is British empiricism. I have no idea actually. I didn't Google it, and I think that this approach is similar to our machine learning models. So we don't store our information on which machine learning models were trained. We store it on the weight. So It turned out that I understood the first proposition completely incorrect, but now I understand it better.
Cool. I'll add, because I do have academic background in philosophy. So there are, back in the day, rationalists and empiricists, right? And the rationalists said, we are born with, let's say, our brain has everything that it needs to interact with the world a priori. So they were big lovers of logic and a priori stuff. Of course, that's like the extremes. It's like a spectrum, right? And on the other side are the empiricists that said, we are born tabula rasa. And then via experience, we interact with the world and we learn stuff. So I guess at the end, it's a combination, right? We're born with something, but from genetics and stuff, but we also learn. So that's why he did this contrast.
Yeah.
So I'll continue. And in this case, the response represents an idea rather than an action. The important feature of this approach is the second approach, is that there is never any simple mapping of the stimulus into memory according to some code which would permit its later reconstruction. Whatever information is retained must somehow be stored as a preference for a particular response, i.e., the information is contained in connections or associations rather than topographic representation.
And what is, by the way, what are these connections in the context of modern machine learning models? These connections is actually weights, because many neural network we can represent it as a graph. So here he's talking about connections.
Yeah,
I'd rather talking about weighted connections. So we see we just can see here the beginning of modern machine learning paradigm.
Yep. By the way, just as a start of this paper, it said higher organisms in the beginning, right, or something like that. And I just want to point out that this term today will never fly in a peer-reviewed psychology magazine.
No. I think paper like this, the chance of seeing paper like this in such mathematical level and such mathematical intricacies and such level of mathematical argument, the chance of seeing in a psychological journal is, very close to zero.
Yeah. And if you see one, they use p-value and they have no idea what p-value is.
Yeah.
Yes.
Okay, but let's continue. So he says, corresponding to these two positions on the method of information retention, there exist two hypotheses with regard to the third question. So the third question, remind you, is given the information stored, how it affects our behavior. So he says, where else? Just a second, I'll find it. With regard to the first question, the manner in which stored information exerts an influence on current activity. Exactly what I said. The coded memory theorists, so it's the first ones, the ones that compares to computers, are first to conclude that recognition of any stimulus involves the matching of systematic comparison of the contents of storage with incoming sensory patterns in order to determine whether the current stimulus has been seen before, and to determine the appropriate response from the organism.
By the way, guys, which machine learning technique, an unsupervised technique, can you see here in this quite long sentence? I think we see clustering here. I get some new vector, and by checking which cluster is the closest to this vector. K-means or any other clustering method, but in essence, it's clustering.
I didn't think about it as in this term. I thought about it more as RAG, like you're actually searching
It's
searching.
more odd. Yeah.
I don't know. Maybe I'm wrong. But
I thought the same. So retrieval augmented generation for the listeners. And the idea there is you have embeddings and you look for using some similarity and find the embeddings.
This reads like search, like actual linear search to me almost. But maybe I'm wrong. I mean, I don't know what he was thinking about. But the coded memory theorist, we know that it's not the prevalent theory these days, and even
So he says the theorist in the empirical tradition, again, the one that says that it's in the connections of the network, on the other hand, have essentially combined the answer to the third question with their answer to the second. Since the stored information takes the form of new connections or transmission channels in the nervous system, it follows that the new stimuli will take use of these new pathways which have been created, automatically activating the appropriate response without requiring any separate processes for their recognition or identification. So again, there's no like a database that you go and read the storage, and then it's like you change the landscape, right? So if you think about it like a hyperplane and you have some function now, and you learn something, so this function changes, and now new information slides differently on this new function, in the hyperplane. It's like you do skiing and they change the slopes.
and this description actually rings to me like multi-layer perceptron neural networks or fully connected neural networks, in which there is an input, let's say an image. He's talking about the vision system, right? So let's say an image, and it flows, activates whatever pathways in the network that are relevant, and it flows like that without automatically, so to speak, even deterministically, and without comparing it to a data.
Yeah. So a cat or a dog, and you get a cat. You never went to a database, right? And I checked. I got the dog out. It just flowed in that direction. So something like that. Now he says the theory to be presented here takes the empiricist or connectionist, right? So I think maybe it's the first time they define this. Connectionist position with regard to these questions. Okay, the theory has been developed for a hypothetical nervous system or machine called Perceptron. So, Mike, you wanted to say something, and I interrupted you.
Actually, I thought about when you were discussing this paragraph, I was thinking about, and now I can explain clearly why I started thinking about it, but I thinking about that we humans are thinking in latent spaces. We are not thinking in a raw data spaces, and I think what we see here is the first hint. I'm not sure if it is a hint, but for me, this paragraph means that kind of Rosenblatt knew it. He knew that. I think from this paper we can with pretty good accuracy tell that he's an apologist of the second approach. And the second approach for me is a latent space approach, which is constantly updated with the new data. When you get new data, you update it. Just you update your neuron network weights. So then I'm not sure I'm fully correct here, but it is just chain of thought which is going.
No, it's really interesting. Because when we see a picture of whatever cat, dog, there's no cat, dog in our brain, right? It doesn't copy it and stores it or something. There is some kind of also latent representation. It's also not stored in the brain. Again, what's stored in the brain the best analog is some kind of neural network. So the weights or whatever may be stored to some degree, or the strength of the connections. So I don't know.
By the way, the same holds also for the language. When we are talking, we are not doing next token or next word prediction. When we start some sentence, they have some, in our mind, they have some latent representation of the sentence we are going to tell. Maybe latent representation of 3 or 4 next words or something like that. They are not operating in a raw space, not in the fiction, and not in the language.
Yeah, for that I agree. I have no idea how it happens, but for sure, again, it's not the raw space, that's for sure. Okay, I'll continue. The Perceptron is designed to illustrate some of the fundamental properties of intelligent systems in general, without becoming too deeply enmeshed in the special and frequently unknown conditions which hold for particular biological organisms. So it's like a general idea. The analogy between the perceptron and biological systems should be readily apparent to the reader. Okay, cool. So he says it's like a general concept. Okay, here he goes about talking the more in depth about the guys that promoted the coded representation idea, and they were affected by symbolic logic, digital computers, switching theory, and he cites them here. And some of them are famous, as far like I've heard about them, Minsky by Neumann. And he says the problem, unfortunately, the language of symbolic logic and Boolean algebra is less well suited for such investigations. The need for a suitable language for the mathematical analysis of events in systems where only the gross organization can be characterized and the precise structure is unknown, has led the author to formulate the current model in terms of probability theory rather than symbolic logic. So that's interesting also.
By the way, there is some model, I don't remember how it was called, which I call a bit level perceptron. In our perceptron, we are going to discuss, the stuff is continuous. But I think 15 or 20 years before it, there was some model, I don't remember how it was called, but what was proposed was bit level proposal. So your weights and also your input and your output are bits, okay, and your operation and or maybe some kind of sum. I don't remember what paper is it, but I suspect that this paper is quite famous. I just can't recall from my old memory what was its name.
This is the ones that he's criticizing, right?
Yeah. Discrete perception, yeah. And the problem with discrete perceptron was that it can't be very easily trained. Compared to the continuous perceptron, with some continuous ways which you can train with your gradient descent or any method of your selection. This discrete perceptron, it can be trained. There are some methods, I guess, evolutionary methods, maybe genetic methods, but it's not so simple as a perceptron which was proposed in this paper.
Got it. So he says he critiques them here, and he says the writer takes the position, on the other hand, that these shortcomings are such that a mere refinement or improvement of the principles already suggested can never account for biological intelligence. A difference in principle is clearly indicated. And he says the theory of statistical separability, which is to be summarized here, appears to offer a solution in principle to all of these difficulties. Let's see. He says, here again, the lack of an analytic language comparable in proficiency to the Boolean algebra of the network analysts has been one of the main obstacles. The contribution of this group should perhaps be considered a suggestion of what to look for and investigate rather than as finished theoretical systems in their own right.
And here he is talking about the point which I arose. These discrete systems can't be easily trained. They can be trained, but it is not so easy.
Perfect.
They can perceive a new information. If they perceive new information means a network configuration, a network request update, it can be hardly done in this discrete perceptron. I think this is what he's talking about here.
And he continues by saying that the theory of perceptron can be summarized as the following. 1, the physical connection of the nervous system, which are involved in learning and recognition, are not identical from one organism to the other. At birth, the construction of the most important network is largely random, subject to a minimum number of genetic constraints. So it's like random initialization, right?
It is, yeah.
Random.
Yeah.
Cool. And then he continues. The original system of connected cells is capable of a certain amount of plasticity. After a period of neural activity, the probability that a stimulus applied to one set of cells will cause a response in some other set is likely to change due to some relatively long-lasting changes in the neurons themselves. Through exposure to a large sample of stimuli, those which are most similar, in some sense which must be defined in terms of the particular physical system, will tend to form pathways to the same sets of responding cells. Those which are markedly dissimilar will tend to develop connections to different sets of responding cells. So it says here there's learning. So now there's a training set, and somehow this weights are changing, right?
Yeah.
Number 4, the application of positive and negative reinforcement or stimuli which serve this function may facilitate or hinder whatever formation of connection is currently in progress. So this is backpropagation, the analogy, or like, right, something like that?
I think it is more even reinforcement learning analogies.
Yeah, that's true.
Rewards, you have penalties, you have positive rewards, you have negative rewards. So it's more, for me, it's more reinforcement learning. Yeah,
there's no backpropagation in this paper. Yes. But there is like feedback, how you change the weights by some kind of reinforcement learning, And then number 5, similarity. In such a system, the similarity is represented at some level of the nervous system by a tendency of similar stimuli to activate the same sets of cells. Similarity is not a necessary attribute of particular formal or geometrical classes of stimuli, but depends on the physical organization of the perceiving system, an organization which evolves through interaction with a given environment. The structure of a system, as well as the ecology of the stimulus environment, will affect and will largely determine the classes of things into which the perceptual world is divided. So that's interesting. What do you think about that?
That's I think that's what we discussed before. Like we have a representation, and we're asking what is in a latent space. What is the closest vector to the representation? Similarity in a sense of similarity, and it doesn't define similarity here mathematically yet, but I think that's the way I think about it, at least.
I'm thinking about different metrics which define similarity, because you can define your distance or similarity, whatever, in many ways. You have some properties must be held, but anyway, you have a lot of choices. So I think then I looking at this paragraph, I'm thinking about different metrics.
Mm-hmm.
Yeah, so I actually quite understand what he says in a similar way that we understand today. So similar, let's say, images of cats, or in general, images of cats, and I have a big network, neural network, will probably activate similar areas compared to the dog. Let's say that's the classifier I had, right? So the cats, although different, are similar because they're activating similar pathways. So that's how I look at it.
By the way, guys, I'm familiar with the polysemantic neurons, about this very cool research which was done by Claude. What is the name of this company? Claude is the model, no?
Not Claude Shannon, I guess. Somebody else.
No, not Claude Shannon.
Anthropic.
Anthropic. Okay.
Model. Yeah, and then trying to understand how our very deep neural nets, our transformer-based large language models, how they're working, and then they came across very interesting. So they just researched it and came to very interesting conclusion. It's the same neuron is activated, is strongly activated for several concepts. You know, the same neuron can be activated for the concepts like car, or for the concepts like computer, or for the concepts like meat. So it is polysemantic and not monosemantic. And here he's talking about, you know, kind of similar stuff. Maybe.
By the way, I'll add to what you said, Mike. Actually, Anthropic called the model Claude because of Claude Shannon.
Ah, really?
Yeah. I googled it. It's true. So funny, huh?
And what is Sonnet called after?
No idea. Yeah. We can Google it again. The listeners can do it.
Okay.
Cool. So let's continue. So now he dives into the organization of a perceptron. So there is like a figure with retina, and then it looks like connections to what's called like A1 and A2 layers, and the last layer is like responses. And okay, our listeners cannot see the photo, but think about it similar to how you look at neural networks today. I think the important part here, it says here, if the algebraic sum of excitatory and inhibitory impulse, so again, the neurons, intensities is equal to or greater than a threshold, then the A unit fires on an all or nothing basis. Okay, so that's like also important concept.
Yeah, where do we have this in actual practical today's machine learning or deep learning?
You know what is defined here in this?
That's the nonlinearity
function.
Yes, that's the nonlinearity plus the bias.
Yes.
So let's say that we have a bias of 0 and a nonlinearity of value, then the threshold is 0, right? We have a bias of -5, the threshold is +5. So it's a natural threshold. And he's talking also about the inhibitory pathways, which is in my mind like pathways that are taking a number that is close to 0, like nulling it out, so to speak.
So like dropout.
I think it's dropout in the sense of training, but in the sense of actual inference, it's neurons that reflect out zeros, like in a ReLU sense. Everything that is, so it inhibits. It physically inhibits the propagation of information to the next neuron.
Yeah.
Got it. So that was emphasize this point because his, let's say, general model has one nonlinearity at the end. Right. So best case scenario, he can linearly separate two classes.
Yes.
Right, because he has one nonlinearity, and I think that was one of the problems because I looked at the critiques of his work. So I think it was Minsky. They said, okay, you cannot learn XOR function. With one nonlinearity. And then it took decades again to like the next idea of doing few hidden layers and making it deep with few nonlinearities or a lot of them. And then you can fit more difficult functions. So that was an important concept.
By the way, Daniel, I think it is more Heaviside function at the end than a Heaviside step function at the end, and not. So yes,
it's a step. He calls it a step function, and we call it a Heaviside.
Yeah. And actually, Minsky, I think in 69 or 70, took 10 years, and he formulated the perceptron as we know it today. So the linear function and a sigmoid, which is invoked on this linear function result, and which actually, as you mentioned, is actually allowed to use this model for some data which is not linearly separate. Yes.
So cool. Well, that's a future paper then.
Yeah.
We're now in 1958 with this one. Okay, so I'll continue. And now there's a lot of pages of derivations and discussions of this model and various excitation. There's like alpha, beta, and gamma modes of operation.
Interesting.
And
look at the Venn diagram here. This is really interesting.
Okay, so figure 2, it says Venn diagram of the same perceptron. Can you describe near what did you find interesting here?
Yeah, I think it's what Mike mentioned before, that sometimes an input will light, so to speak, or activate an area in the neural network. I don't want to say the brain, but this is implied here in this paper, and also activate another area at the same time, or a part of another area. Okay, and this is what the Venn diagram is mentioning here. That is, the areas can overlap, and sometimes even be masked. So, for example, the circle, the bottom circle in this Venn diagram, which I can't read its letter here, is partially lighted by the top circle.
Yeah, also for me it's hard to read.
Yeah. This paper is hard to read in the font. It's
okay, I'll continue.
Yeah.
And let's see the important parts. Here he starts to formalize his model, meaning put it into math and equations and define stuff. Okay, so again, we won't go over everything, but here he's got his main definition. P alpha, the expected proportion of A units activated by a stimulus of a given size. So A units is like the first, let's think about it as the first layer of this perceptron neural network.
That's A is for association.
Cool.
So it's called association units, yeah.
And here he has like a binomial distribution, right? Because it could be in different states, etc. And then he sums everything, and there's a lot of summing going on here. And again, when I went over it, I'm like, okay, I believe him.
By the way, guys, when I was reading this for the first time, I think it is unrelated, and I'm trying to talk with Sonnet about it. You know that the binomial distribution can converge then under some conditions to two non-degenerate distribution. It can converge to the normal distribution, and it also can converge to the Poisson distribution. Poisson distribution, which is sometimes called the small numbers law or something like that. I don't remember. Then the p multiplied by n tends to 0 maybe. I don't remember. And here in this paper, when I continued to read this paper, I saw some normal distributions, but I was not able to connect these formulas with this normal distribution that came after in this paper. Maybe you guys can share your thoughts. What do you think about it? Because I'm not sure it is accidental.
Mm-hmm. I don't know. I have to think about it.
Okay.
Yeah, I didn't go there even.
Okay.
I'm just like, okay, I understand why it's binomial, because some are excitatory, some are inhibitory.
Exactly, yeah.
And depends, and then let's do all the combinations.
Yeah.
So you have all the different combinations of stuff. So that's what I looked into.
Yeah, in order to understand it, you need to go deeper in this very famous movie.
Yeah.
Yeah,
And equation 2 here is, I guess, the conditional probability that an association unit which respond to one stimulus, S1, so to speak, will respond also to a second stimulus. And that goes back to what Mike said before, that sometimes a similar one unit or one neuron can respond both to cat and a dog in the decision process.
Yes.
Like, for example, they're all animals. Okay, that's the meaning of this Venn diagram that he mentioned.
By the way, maybe the same area in our brain, the same small area in our brain can respond to very unrelated concepts like our LLMs do, according to the anthropic research. I'm not sure. I'm not a big specialist in brain sciences, in psychology, but no, not psychology, brain. What
neuroscience,
neurophysiology, right? But it is interesting to check.
Got it. Okay, so I'll continue. And then he does some plots to investigate those formalism under various conditions of a threshold, etc. The threshold for firing and others. So we won't go into this. Then he goes to a chapter named Mathematical Analysis of Learning in the Perceptron. Okay, so now we have some kind of, we talked about it, the idea of reinforcement learning. So you get either positive or negative feedback.
By the way, this term learning in the context of machine learning, or in the context of in the context of, let's say, in the context of machine learning, maybe it's one of the first papers which used this term to actually describe what is being done during the training. Because learning, we are learning as humans, we are learning, and here it is. I don't remember out of all papers we talked about, which more or less all of them were somehow connected to machine learning. I can't recall the term learning was used. Maybe it is one of the first time which it is worth checking, but sure.
Yeah, so a lot of concepts that we use today, also it talks about generalization. At some point, he talks about like doing
Yeah, you have a
training.
normal integral, normal curve integral, yes.
I have a question. When he's talking about increased inhibition, did you guys, when you read that, did you guys think about regularization at all?
Actually, I don't. Actually,
No.
I didn't think about it at all.
Maybe weight decay or something.
Yeah, but weight decay it is a fancy name of the regularization. For those who can't say regularization because it is a very long word, you know. Weight decay. What is weight decay? It is some kind of regularization L1 or L2. I don't remember. Maybe both. By the way, it is interesting. So you want is the more strong regularization you have, the more you want to inhibit the weights, you know, the weights of your system. It is interesting to think about it. Yeah, it is an interesting direction of thinking. Yeah.
Okay, then he has a chapter named bivalent system. So I think now the feedback can be positive and negative. I think previously it was just negative. Here it says in a bivalent system, two types of reinforcements are possible, positive and negative. Okay, so previously he was analyzing only, I think, negative or positive reinforcement.
I think he's talking about something which reminds me a lot the binary classification. So all this inhibition and what is the converse of inhibition?
Inhibit and excitatory, exciting.
Yes.
Neo, maybe you know better. You're
excitation and inhibition. Yeah.
Yeah. How?
Excitation and inhibition.
Okay. As excitation and inhibition, we can look at it as two binary classes of plus and minus one. You know. And for example, even more than in the reinforcement learning, maybe reinforcement learning is not so good analogy. And the better analogy is just the binary classification. You know, you're just moving your weights in order to distinguish in the best way between the +1 and -1 classes. So here you have excitation and inhibition, +1 and -1. You know, here I think he's talking about 1 or 0 because inhibition, and then we see this word inhibition, they are thinking about 0. But essentially, these are two very similar concepts.
Yeah, of course. Of course, the whole analysis of Bernoulli binomial is based on the +/-1 or 0, 1. That's really, yeah.
So here we got to the chapter of conclusions and evaluation. And he says when the stimuli is random, meaning we randomly connect units, etc., or show like random data, it says in such environment, no basis for generalization exists. Makes sense?
Yeah.
Then he defines like environment when they're actually like different classes. And then he says, oh, the system can learn, which makes sense. Again, to us, it sounds self-evident. Back in the day, it was something like new and novel.
100%.
Then he says the important thing, trial and error learning is possible in bivalent reinforcement systems. So again, when you can do positive and negative, as we said, like binary classification. I like number 9. The memory of the perceptron is distributed in the sense that any association may take use of large proportion of the cells in the system. And the removal of a portion of the association system would not have an appreciable effect on the performance of any one discrimination or association. So it's also cool. Like, right, if you lose part of the network, still mostly works.
Yeah.
Which is true to us, right? So if you burn like 5 transistors in your motherboard on the laptop, that's a big problem. In our brain, we lose all the time stuff, neurons, right? Like it's, some people lose half their brain and then can learn again some stuff. So this is an important point in my opinion.
Yeah.
By the way, which it proves that our brain is some kind of I don't remember what is the exact name of this autoencoder, but there is a specific type of autoencoder that then you add noise to your data, and you are trying to learn a latent representation of your data, which allows you to filter out this noise, denoising autoencoder. So our brain is a very cool denoising autoencoder, so we can lose. There are different types of noises. You know, there is noise, there's Gaussian noise, and it is, and you have also pepper salt noise in the computer vision.
Mhm.
Maybe pepper salt noise in our brain is just dead neurons. So for me, our brain is a quite efficient denoising autoencoder.
Cool, Mike. Yes, sorry, Neil. Let's go over an important pushback, or he thinks about future pushback he's gonna get. So he says, psychologists and learning theorists in particular may now ask, what has the present theory accomplished beyond what has already been done in the various theories of, he names the people. So now he says, okay, great question, I'm gonna answer it. Number one, parsimony, meaning it's when you have a model which is small that explains a lot, right? So it's similar to Occam's razor, right? Makes sense. And he says here, essentially all of the basic variables and laws used in the system are already present in the structure of physical and biological science. Okay. Number two, verifiability, meaning you can verify this, let's say, model. Previous quantitative learning theories, apparently without exception, have had one important characteristic in common. They have all been based on measurement of behavior in specified situation using these measurements to predict behavior in other situations. Such a procedure in the last analysis amounts to the process of curve fitting. So he says they're doing like overfitting.
Yeah.
And extrapolation in the hope that the constants which describe one set of curves will hold good for other curves in other situations.
Yeah, and he's talking about what we are doing, what we all are doing in the modern machine learning. We are training our models on some data, on some data sets, and then we are trying to use it for on different data, and we hope that the model will generalize. What does it mean, generalize? Extrapolate, because we didn't see this data, so the model should somehow should learn some inherent features of our data, and then we hope that during our training the model has indeed learned.
No, but look, Mike, he says here his claim is that they're actually doing overfitting. Look, he says that such extrapolation is difficult to justify in a new situation, and it has been shown that if the basic constants and parameters are to be derived anew for any situation in which they break down empirically, such as change from white rats to humans, right? So they took a model, fitted on rats, and tried to check it on human. And he says, then the basic theory is essentially refutable. So if there's a theory with a lot of parameters and you overfit it on rats, right? It won't work on human.
Yes.
It says, as any successful curve fitting equation is irrefutable. So he says that's the problem. You can invent theories with a lot of parameters, overfit them on new data, and then it doesn't work on new one. What I don't understand, why can't you do the same on his model? It has also a lot of parameters. In theory, you can overfit also.
You have two different options here. There is a concept which is called continual learning, and you are trying to learn your model different capabilities. You just train your model to distinguish between dogs and cats, and then you want to to train or to adapt your model to distinguish between dolphins and whales, for example, and it is not always simple. And in many cases, we just prefer to train different models, or to retrain these models from scratch to distinguish between all these categories together. And he's talking, and this is actually he's talking about the concept of continuous learning, continual learning. Sorry.
Good point, Mike, and it is useful. Also called, I think, active learning, right?
Active learning.
But,
active learning is a bit different. It's a bit different concept, because active learning, you have a lot of data, and you try to choose
which training.
To pick the most valuable, and from the training point of view, from your accuracy, from the final accuracy of your model point of view, data. So it is a bit different concept, I think.
And look, I like this quote. Again, he's attacking like the overfitting that people are doing. In considering this approach, one is reminded of the remark attributed to Kistiakowsky that said, "Given 7 parameters, I could fit an elephant."
Yeah.
To understand it, you need to define what does it mean to fit an elephant.
Yes.
I'm not sure I fully understand it. What does it mean to fit an elephant?
Yeah, I think that what he argues here is that the perceptron model, as he defines it, which is a probabilistic model, I guess, the independent parameters are not simply conforming to the data. They're and thus they're more poised to predict behavior than actually just conform to the data and on overfit. I don't think that this is true in our current knowledge of what's happening inside the perception neural networks, but that's what he thinks.
Yeah, got it. I agree. Number 3, again, he claims why his method is good. Explanatory power and generality. Because the present theory being derived from basic physical variables is not specific to any one organism or learning situation. It can be generalized in principle to cover any form of behavior in any system, etc. So I think we agree here, right? Because it's really general idea.
Yeah.
Okay, next point. That was number 3. I think that's it.
I think the last paragraph is worth reading. What do you think, Daniel? The last paragraph worth reading.
Okay, cool. Let's do the last paragraph. Yeah. The present theory represents the first actual completion of such a bridge. Through the use of the equations in the preceding sections, it is possible to predict learning curves from neurological variables, and likewise to predict neurological variables from learning curves. How well this bridge stands up to repeated crossings remains to be seen. In the meantime, the theory reported here clearly demonstrates the feasibility and fruitfulness of a quantitative statistical approach to the organization of cognitive systems. By the study of systems such as the perceptron, it is hoped that those fundamental laws of organization, which are common to all information handling systems, machines and men included, may even truly be understood.
It is a very powerful sentence. The last sentence is really powerful. And it came true actually now, We are using perceptrons, now we are using transformers, but still perceptrons are in wide use,
Yeah. The concept of perceptron is everywhere, right?
Yes.
Even in transformers, even in convolutional neural network, the same concept of linear combination and nonlinearity.
Yeah.
And all of the probabilistic representations of everything is widely used, and we are observing. We are biased, so we are observing this paper, and our brains are automatically doing what we call an anachronism, right? Which is we're judging this paper based on what we know today, but he didn't know all this stuff. So this is
Mhm.
remarkable. Yeah.
True. It is like amazing to read it in retrospect. Actually, when you said it now, Nir, I thought about the other paper we covered, the logit function and the logistic regression.
Mm-hmm.
And like I would have presumed he had somehow in his analysis he would mention maybe not logistic regression, but you know, doing some kind of curve fitting and anything like that, because in a sense his perceptron also there he called it reinforcement learning and you teach etc. But he knew and others knew back in those times how to do, you know, least squares etc. So I wonder why he didn't mention that, or he didn't do the connection.
Yeah.
You understand where I'm going with that?
I completely understand. I think that his this paper specifically. I mean, this is my view. Maybe I'm wrong, but it's not. It's not like I can prove it on the whiteboard. What I'm saying is trying to be as general as possible and not propose any restricting functions. So he's modeling everything probabilistically in an excitation and inhibition model, or ones and zeros, and I think that it doesn't matter what kind of nonlinearity, for example, you use.
Yeah.
You can still this model still holds, and that brought him to this powerful conclusion that you just read. I think because you can put the logic or you can put another nonlinearity, but still at the end of the day, it's just probabilistic measure. That's what I understand from that.
Got it. Cool. So that was this paper of the Perceptron. I now reminded myself that we never say hit the like button and share, etc. So I will subscribe. That would be cool. Thank you, Mike and Nir. And see you,
one
everyone.
small remark. You mentioned it, I think after this episode, our listeners who hasn't yet watched our episode about logistic function, I think it is the second or third episode. I think it is a great moment to watch this episode and to compare with concepts because they're similar and I think watching this episode about logistic function can be quite enriching after watching this episode. At least my opinion.
100% agreed.
Cool. So if you didn't watch it, and see you everyone next week.